So I'm going to start in right where we left off last class period to finish up the chapter on aldehydes and ketones, talking a little bit more about the concept of stereochemistry or stereoisomers, which when we define what we're talking about when we refer to stereoisomers, we're referring to specifically the type of isomer, that is two molecules that have the same number and type of atoms, but have a different three-dimensional structure. So everything about the molecule is the same except how the individual atoms or groups are oriented in three-dimensional space. So when we're talking about stereoisomers, we're referring to molecules with the same molecular formula, but a different three-dimensional shape, or something different about their three-dimensional structure. So they would have the same IUPAC name with the exception of some way of designating what the three-dimensional shape of the molecule is. So stereoisomers basically come in two types that we will talk about. And those two categories that we can break stereoisomers down into are what we refer to as diastereomers and the other type of stereoisomer is the enantiomer, which we had the example in class last time of the two molecular models that were related as enantiomers, where enantiomers are defined as molecules that are related to one another as non-superimposable mirror images of one another, much like your left and right hand. So these molecules that are related to one another, those non-superimposable mirror images, in order for that to be the case, the molecule that you're looking at has to have what we refer to as a chiral center. That's a prerequisite for a molecule to have a non-superimposable mirror image of itself. So in order for a compound to have an enantiomer, the compound has to have a chiral center. That is a carbon atom that has four different groups bonded to it. So a chiral carbon means that it has four different groups bonded to the same carbon atom. And so an example that we could look at of a chiral molecule would be the example of lactic acid. And to show the chirality of a molecule, what we do to indicate it is we indicate it as wedges and dashes to indicate the three-dimensional structure of the molecule. So a wedge is a bond that points out of the page, it points toward you. On the other hand, a dash is a bond that points into the page, it points away from you. So that's showing how the atoms are oriented in three-dimensional space in order for us to understand this concept of enantiomers. So when we're talking about a carbon that has four groups bonded to it, and in the case of enantiomers, four different groups, the way that we can show that carbon, keeping in mind that the carbon is an sp3 carbon, has four regions of electron density around it, and those four regions of electron density, to space those out as far as possible, the molecular geometry of the carbon is going to be a tetrahedron. And so to draw a tetrahedral carbon, what is basically shown is that two of the bonds are going to be in the plane of the page, meaning they are basically sitting right there at the page. So I'm showing those in orange here by highlighting. So those two bonds that I've just outlined in orange are the bonds that are in the plane of the page, we would say. Then one of the bonds is pointed out of the page, aimed toward us. That's what we show as a wedge. So that's what I'm showing here as the wedge coming out of the page. So that wedge, shown in pink now as I'm highlighting, points toward you. And then the bond pointed away from you into the page is what we're showing as the dash. So dash is basically a dotted line. So we use this to illustrate in our molecule the stereochemistry, and it's particularly useful for illustrating two different enantiomers of a particular molecule. So for example, if we go ahead and make a chiral center here, we're going to have our carbon. I'm going to show my wedge here that I'm shading in just now, and then my dash going away from us. In order for this to be a chiral carbon, it has to have 4 different groups bonded to it, and so I'm going to show those 4 groups in blue. So for example, we could do a methyl group, we could do a ethyl group, we could do a hydroxy group to make this into an alcohol, and we could do, for example, a hydrogen here. So now our carbon there in the middle, which I'll use a star to denote that that carbon is a chiral center, has 4 different groups bonded to them. We're showing how those groups are oriented in 3 dimensions by using these wedges and dashes. So when we're showing the tetrahedral carbon, that is the carbon that has 4 different groups bonded to it, to show the stereochemistry of that, we use 1 wedge, 1 dash, and 2 lines to illustrate that. So now if we want to make the enantiomer of this molecule, what we do is envision that we put in a mirror, which I'm showing with this green dash here, and we envision what would we see on the other side of that mirror. If the molecule looked at itself in the mirror, what would it see basically? And so if you look at your left and right hands and hold those up to one another as mirror images, you're going to see that your thumbs are pointed toward one another. So if we think of this wedge here as being the thumb of the molecule, if on the image on the left, the thumb there is pointed toward the center, aimed toward the right, then when we go over to the mirror image, that thumb, the wedge that is going to have to instead be aimed to the left. So we'll go ahead and fill that in. The dash that we're showing here in our starting molecule is still going to be a dash in the enantiomer in the mirror image, but it's going to be oriented in the opposite direction. So rather than pointing up into the right, it's going to be pointed up into the left as I've just drawn. And then the line that's pointed straight up in the mirror image would still be pointed straight up in the enantiomer. That's not going to change. If you hold your hand straight up and you look how your fingers are oriented straight upward, in the original structure of the mirror image, it's still oriented straight upward. And then the bond that's a line there angled to the left on the structure on the left is going to instead be angled to the right on the other one. So we're just basically drawing in our mirror image here. So these 2 structures are related to one another as what we refer to as enantiomers. And anytime we have a molecule that has 1 or more chiral centers, chiral carbons, it's always going to be the case that there will be 1 enantiomer possible for that molecule. In other words, enantiomers always come in pairs, meaning that you have the original object, the original molecule, and its mirror image. So a molecule can have at most 1 enantiomer, and in order for that to be the case, that molecule has to have a chiral center of a carbon that has 4 different groups bonded to it. If instead there's not 4 different groups bonded to it, that molecule is not going to have the possibility of having an enantiomer. So that's a general topic of enantiomers. We're going to look at that a little bit later because we're going to look at how we would go about drawing different enantiomers of a particular molecule and how we could use words to express which specific 3-dimensional structure we're referring to here, because what we're often going to see is the case is that the biological functions of molecules definitely differs based on which enantiomer you're dealing with. So this concept is really important in determining how molecules interact with biological systems, because most components of biological systems, such as enzymes for example, are elaborate 3-dimensional structures, and so the small molecule that's coming in and interacting with those needs to have a 3-dimensional structure that is perfectly complementary to the 3-dimensional structure of the protein, much like a hand fits in a glove. And so this concept of enantiomers is very important in drug discovery. It's also important in terms of whether vitamins are effective or not. Typically the correct stereochemistry has to be present in the vitamin molecule for it to be effective, and enantiomers come into play in a wide variety of other things as well. So that's enantiomers. And then while we're on our general flow chart here of stereoisomers, we should also mention the concept of diastereomers, going back to this second type of stereoisomer. So we said that enantiomers were two molecules related as mirror images of one another. Diastereomers, on the other hand, are basically every other possibility when it comes to stereoisomers, when it comes to molecules that have the same molecular formula but some difference in terms of their three-dimensional structure. So an example of diastereomers would be referring to cis and trans molecules. So we talked about this, for example, back in the chapter on alkenes, where I believe we referred to these two as related as stereoisomers, but we didn't specifically go down the flowchart quite enough to refer to them as diastereomers. Diastereomers is the most specific term. So if you had two molecules, such as this compound versus the one I'm going to draw here, and you were to come up with an IUPAC name for those, you would establish the same IUPAC name for each of them, with the exception of the designation of cis or trans. So remember, to assign cis or trans, you look for the longest carbon chain coming through the molecule. That carbon chain has to include the alkene group. And then you ask yourself, relative to that alkene group, shown here, do the two bonds that are part of the longest carbon chain, that is the bond here and the bond here, are those oriented on the same face of the molecule, meaning they're pointed both down or both up, or are they opposite? And if they're opposite, such as is the case here in light blue, then we refer to the molecules as being trans. If they go the same direction, we refer to them as cis. So over here, following our longest carbon chain, you'll notice that relative to the alkene group here in the middle, both of those bonds going away from that part of the longest carbon chain are going in the same direction, so we'd refer to this molecule on the right as being cis. And so these two molecules are related to one another as diastereomers. Definitely they have a three-dimensional shape difference, but other than that three-dimensional shape difference, the molecules are the same in terms of which atoms are bonded together. So in both cases, at carbon number 3 of the chain, there's a methyl group bonded there. And so they have the same molecular formula, same overall IUPAC name, with the exception of what the stereochemistry is. So diastereomers are generally referring to the cis and trans forms of molecules, such as is the case here with the alkenes. So that's diastereomers. We're not going to go into too much more detail on that, since we already looked at that a bit earlier in the semester with our alkene chapter. What we are going to look at more now is this concept of enantiomers, and specifically how we can go about drawing enantiomers and using words to represent which enantiomer we're referring to, because since the different enantiomers do have very different biological effects, we need to be able to clearly and distinctly refer to a specific enantiomer. And so we're going to talk now about how we would go about specifying which enantiomer of a particular molecule that you are dealing with. And the way that we do this is by using what we call RS nomenclature, or the RS system, to represent stereochemistry, to represent specifically what enantiomer we're dealing with. So the RS system will be used to specify the stereochemistry, or we could also refer to it as the chirality. And when we're talking about this, we're always going to be referring to a specific carbon atom. So each chiral center in a molecule will have the opportunity to be what we refer to as the R stereochemistry or the S stereochemistry. These are the two possible ways that the molecule could be oriented in 3 dimensions. So R versus S refer to the two different enantiomers at a particular chiral center. So when we're referring to this RS designation, that's going to indicate to us which molecule we're referring to. For example, up here when we talked about these two molecules that I'm circling in red here, being related to one another as enantiomers, we should be able to describe in words which one of those is which. And so we're going to go through and try to accomplish that by using this RS designation or RS nomenclature. So in order to assign the stereochemistry to a particular molecule, what we're going to do is follow some rules here for looking at the chirality of a chiral center. We're going to call it R or S to refer to the stereochemistry of it, to refer to the three-dimensional orientation of atoms around that chiral center. So first thing that you're going to do is you're going to go in and you're going to rank or prioritize all of the groups that are bonded to that chiral center. So first thing first, we're going to rank the 4 different groups. It'll always be 4 groups because remember, to be a chiral carbon, it has to have 4 different groups bonded to it. So we're going to rank the 4 groups that are bonded to the chiral center. And the way that we're going to determine how we go about ranking that is by this. Atoms with a higher atomic number will take higher priority. So if you look at the periodic table, find the atomic number for the atom that you're interested in. For instance, carbon's atomic number is 12, hydrogen's atomic number is 1. You're going to take the one that has higher atomic number as having higher priority in assigning the rank of these 4 groups. So basically here, the higher the atomic number from the periodic table is going to correspond to higher priority in this ranking system. So this is basically a systematic way of ranking the groups around the chiral carbon so that we can establish which stereochemistry the molecule is, which of the 2 enantiomers it is. So for the molecule up here, what we do to assign the rank based on atomic number is we look at the 4 groups that are bonded to the carbon, and specifically we look at the atom that's directly bonded to the chiral carbon. So our chiral carbon is here in the middle. I just highlighted that one in pink. And then we ask ourselves, what atom is directly bonded to that chiral carbon? Which 4 atoms are directly bonded to that chiral carbon? So we have an oxygen, we have a hydrogen, I'm highlighting these in pink, we have a carbon that's part of a methyl group, and a carbon that's part of an ethyl group if we were to draw this out and ask ourselves exactly which of these atoms is bonded to the chiral center. So if we look at the chiral center, there are carbon, that is our chiral carbon, that has that red star next to it, is directly bonded to an oxygen, hydrogen, and 2 carbons. So to rank those 4 groups based on atomic number, we can relatively easily rank the oxygen and hydrogen relative to one another and relative to those 2 carbon atoms. So looking at the atomic number of oxygen is greater than the atomic number of carbon. And so oxygen gets a higher rank. And so I'm going to just put my ranking number here in green beside that atom. I'm going to rank my oxygen as atom number 1 here. It's the highest ranking because it has the highest atomic number of the individual atoms that are bonded to the chiral carbon. Then hydrogen certainly has a lower atomic number than either carbon or oxygen, so I'm going to rank it as number 4. We're basically ranking the groups 1 through 4, where 4 is the lowest atomic number atom, 1 is the highest atomic number atom. And then we run into a little bit of a problem here with our carbons because we have a methyl group and an ethyl group, both of which have a carbon directly bonded to the chiral center. And so we're not going to be able to immediately use this rule of increased atomic number means higher rank because we have 2 identical atoms there. Even though the groups as a whole are different, meaning we have a methyl group versus an ethyl group, the first atom that we come to when we go away from the chiral center is the same in both cases. So we need to look a little bit deeper about how to rank the ethyl group relative to the methyl group. And the way that we do that, coming back down here to our list of rules for ranking the groups that are bonded to the chiral center, is that if the atoms directly bonded to the chiral center are the same, such as is the case here with the 2 carbon atoms, then what we do is look 1 atom further down the chain, going away from the chiral carbon, and assign the priority based on the first atom that we find that will allow us to differentiate between the two groups. So we're trying to look for a point that is different between those two groups, between the methyl group and the ethyl group in our case. So the criteria here is if the atom that's directly bonded to the chiral carbon are the same, we look one spot further down the carbon chain to find some point that we can use to differentiate between them. We look for the first atom that is different between the two groups. So if the atoms directly bonded at the chiral carbon are the same, what you'll do is look one spot further down the carbon chain, going away from the chiral center in order to figure out how they differ. So you're going to look further down the chain, away from the chiral center. So you're going to move basically one atom further down the chain. So in the case of, looking back up here at our example of ranking the four groups that are bonded to our chiral carbon here, we have our ethyl group versus our methyl group. In the case of the methyl group here, the methyl group has a carbon directly bonded only to hydrogen. So the second spot going away from the chiral carbon, first spot was that carbon from the methyl group, second spot is a hydrogen. So for this CH3 group, the second atom moving away from the chiral center is going to be a hydrogen. On the other hand, if we come over here to our ethyl group and we ask ourselves, moving away from the chiral center, what's the highest ranked atom as we move one spot further away? So our first spot was a carbon, and we move one spot further away down the chain and ask ourselves what the highest ranked group there is, it's going to be a carbon atom. So we can rank here, then the second atom that we see coming down the chain is a carbon atom. And so carbon definitely has a higher atomic number than hydrogen does. And so that carbon is going to result in the ethyl group getting a higher rank than the methyl group. So we already said the hydroxy group was ranked 1, so that's going to leave our ethyl group at number 2, methyl group at number 3, and our hydrogen atom at number 4 there. So now we've ranked those four groups that are directly bonded to the chiral center, and we can do the exact same thing for the enantiomer over here on the right. So I'm just going to fill in those rankings the same way. The same system is used to assign these. So 1 is the hydroxy group because that oxygen has the highest atomic number. 2 is the ethyl group because the ethyl outranks the methyl group because the second carbon in the chain in there has a higher atomic number than if we were looking at the methyl group, instead has just the hydrogens there, which have a lower atomic number. And then the fourth ranking group, the loser there, is that hydrogen atom. So we've ranked the four groups directly bonded to the chiral center of both of those two enantiomers. And then what we're going to do to assign the stereochemistry here as what we refer to as R or S, looking at our second guideline for determining which chirality we're dealing with, we're going to rotate the molecule as needed so that the lowest ranked group points away from us. So the lowest ranked group has to be on a dash rather than on a wedge or on a line. So rotate the molecule if needed so that the lowest ranked group points away from you. In other words, if the lowest ranked group points away from you, it's what's going to be shown as a dash. And generally for purposes of this class, I will go ahead and pre-orient the molecule for you so that the lowest strength group is indeed pointed away from you, so that you won't generally have to deal with this point 2 of rotating the molecule so the lowest strength group points away from you. And if we take a look at the molecules that are shown up here that I'm using as my example, it's no coincidence that I pre-organized those molecules for you so that the hydrogen, the lowest strength group, is indeed a dash. It's pointed away from you. So we're good on that. Lowest strength group is pointed away from us. And then we come to our third point here in assigning the chirality of this molecule as R or S. What we're going to do is draw a circle from starting at the highest ranked group and continuing to group 2 and group 3. And we're going to determine whether that circle that we're drawing goes in a clockwise or counterclockwise direction. So looking at it, we're going to draw a circle starting at the highest ranked group. So basically starting at what we're referring to as group 1 and going then secondly to group 2 and then thirdly to group 3. And based on that information, if the direction that we're going and going from 1 to 2 to 3 is clockwise, so clockwise we'll abbreviate here as CW, so if the circle is clockwise, CW, then the molecule is referred to as R. So R meaning basically right. So clockwise means moving toward the right, so if we're going clockwise in our circle there, we refer to it as the R enantiomer. If, on the other hand, we're going counterclockwise, which I'll abbreviate as CCW for counterclockwise, instead we refer to this enantiomer as being the S enantiomer. And the S is basically based on the German word for left, which in German starts with the letter S. That's going to indicate that we are going left or counterclockwise. And so if we come up here and we attempt to assign these two enantiomers as R and S, if two molecules are related to one another as enantiomers, one will always be the S chirality and the other will always be the R chirality. Enantiomers are always related as pairs of R and S. So what should be the case here, if I've drawn these enantiomers correctly, is that one of them should come up assigned as R and one should come up assigned as S to confirm to us that these are indeed enantiomers. So the R and S allows us to write in words which of these two three-dimensional structures we're referring to here. So going from highest ranked, number 1, then to number 2, and then to number 3. For our structure on the left there, as I've shown in orange, going from 1 to 2 to 3, first highest ranked, second highest ranked, third highest ranked, takes us in a counterclockwise direction. So we would refer to that structure on the left as being the S enantiomer. On the other hand, if we look at the structure on the right, when we go from group 1 as our starting point, then pass through group 2, and end up at group 3, we are going in a clockwise direction. So we'd refer to that enantiomer instead as being the R enantiomer. So I'm going to go ahead and put R in there to indicate to us that that is the R enantiomer there that we're dealing with. So that's our R enantiomer there on the right. We've assigned using those rules that we just went through. And so we know that these two molecules are related as enantiomers because we see that they have the same number and type of atom, the same atoms are connected to one another in each case. The only difference is how the atoms are oriented in space. And if we go through and systematically assign R or S at the chiral center, we see that the chirality is flipped in going from one to the other. So that's how we know that these are enantiomers. We can go through and systematically assign one as S and the other as R, and that will indicate to us that they are indeed enantiomers. And this is a trick for doing this even if the molecule is rotated kind of funny so that they aren't lined up exactly like this, so it's not as easy to tell that they are indeed mirror images of one another. You can always go through and systematically assign the stereochemistry at the chiral center, and if the stereochemistry of one pops up as R and the other pops up as S, you know straight away that those two molecules are enantiomers as long as they have the same number and type of atoms. In other words, as long as the IUPAC name is the same between the two, with the exception of terms designating stereochemistry. So in the case of these two molecules, we could come up with a complete name for each of them, including the stereochemistry. And so we can do that for each of these two molecules here. I'm going to go and erase a little bit of this info here if possible so that we're not quite so cluttered up here. Try to erase some of it anyway. So what I'm going to do is fill in the IUPAC name for each of these, including stereochemistry. So you might occasionally run into a question where it would say, provide the IUPAC name for a molecule, including stereochemistry. And if it indicates that, you need to definitely be specifying whether the molecule is S or R, or if it were an alkene, you would need to be telling me whether it was cis or trans. That's what we mean when we say mention the stereochemistry in the name of the molecule. So we learned about alcohol nomenclature a couple of chapters back. So in thinking about that, our structure on the left here, if we look for the longest carbon chain in that particular molecule, we can see that we have a methyl group at the right hand end here, connected to our second carbon there. So we have our methyl group connected to our second carbon, and then over to here would be our longest carbon chain now that I've kind of mapped out in light blue. So our longest carbon chain is 1, 2, 3, 4 carbons. So our parent name here would be butane if it were an alkane, but since it's an alcohol, it's butanol. And at carbon number 2 of the chain is where we have the hydroxy group. That's where our alcohol group comes off of the chain. We start, remember, from the end closer to that methyl group because that's the end closer to the alcohol group. So carbon 1 is our methyl, carbon 2 is the one that has the hydroxy group, so that's why we call it 2-butanol. So that accounts for our entire chain there, and basically accounts for everything in the molecule except the stereochemistry. So to specify the stereochemistry, what's generally done is that immediately before that general IUPAC name that we've talked about previously, you put the designation of stereochemistry. So the structure on the left here, if we were asked to provide the IUPAC name for that, it would just be S2-butanol, where S is indicating the chirality of that molecule. It is possible you would run into situations where a molecule could have more than one chiral center. And if that were the case, you would need to specify the chirality at each chiral center, at each chiral carbon, in the prefix of the name. And to do that, you would indicate what carbon number had a specific chirality. So we could also call this 2S2-butanol because the chiral center is at position number 2. But in this case, since there's only one chiral center in this molecule, it's not necessary to put that number 2 in there to indicate exactly where the chirality is, since there's only one position of this molecule that it could possibly be located at. But if you have a molecule that has more than one chiral center, then you're going to have to indicate where the chiral carbons are when you designate the R and S in the prefix of the name. The name of the molecule on the right-hand side here would be the exact same with the exception of stereochemistry. So rather than being S2-butanol, referring to the molecule on the left, the molecule on the right would be R2-butanol as the IUPAC name of that, including the stereochemistry. We can also apply this information towards some other molecules as well that aren't drawn out quite as explicitly. So the example we just looked at had the molecule drawn as a full tetrahedron. We specifically showed around that chiral carbon wedges and dashes to every single group that was bonded to it. It is also very common to show chirality for molecules as part of line angle formulas. And generally, if they're shown as part of line angle formulas, what is done is that the groups that are branching off of the carbon chain, so we'd have the carbon chain there shown in the plane of the page, and then a group that's branching off of that would be shown as a wedge or a dash. So for example here, we could do the case of a alkyl halide by putting a chlorine in there. And if we look at this molecule and you ask yourself how many chiral centers there are, I'll go ahead and plug another one in here just for good measure. You could be asked a question like, how many chiral centers are there? Or how many chiral carbons? And you might be asked to identify each of those chiral carbons as R or S. And so tackling this problem, remember that a chiral carbon is a carbon that's 4 different groups bonded to it, and any carbon that's a chiral carbon will be assigned as R or S. So if we look at this molecule, anything that's a CH2 or CH3 group is definitely not going to be a chiral carbon, so we can basically ignore the methyl groups and the CH2 groups along the chain here. Then we need to focus in on the locations of the molecule where we have 4 groups bonded. So if we look at the carbon that I just put a star on, we would see we have 4 groups bonded there. The methyl group, the long carbon chain going away from it, the hydroxy group, and then remember that in a line angle formula, the carbon-hydrogen bonds are implied, and so there's also a hydrogen atom here that we're not showing, and that hydrogen atom would fill in the last remaining piece of the tetrahedron. So remember, when we're drawing a tetrahedron, we have 2 lines, a wedge and a dash. So here we have 2 lines and a wedge, so what's missing is the dash, so it's implied that there's a hydrogen atom there as a dash pointing away from us. But that generally will not be shown to you. That's something that you have to know, that you'll fill in based on your knowledge of line angle formulas. So similarly, if we come down to the other end of the molecule here, we have our carbon directly bonded to an ethyl group, directly bonded to a chlorine, directly bonded to this relatively long carbon chain that has the hydroxy group toward the end of it, and we also have that bond to the hydrogen that we're not showing. And you can point that as a wedge to the left, wedge to the right. It actually doesn't matter in terms of what the stereochemistry R or S is going to turn out to be here. So the information that you have available there in black is plenty sufficient for assigning R or S to this, even if we don't explicitly show the hydrogen atoms there. But be aware that the hydrogen atom is that missing piece of the tetrahedron, and in these cases the missing piece of the tetrahedron is the bond that points away from you. So I'm going to go ahead and erase those hydrogens, since we're going to go in and assign the chirality here. And to assign the chirality, remember that we rank the 4 groups, 1, 2, 3, 4, where the lowest ranked group is pointed away from us. So in this line angle formula, the convenient thing is that in this structure, the hydrogen, the lowest ranked group, hydrogen is always going to be the lowest ranked group since it has the lowest possible atomic number, is pointed away from us at both of these chiral centers. So we can just basically ignore it because it's definitely going to be spot number 4. So we just need to rank these other 3 groups that are bonded to each chiral center relative to one another as we look at criteria number 1 up here of our criteria for assigning chiralities are. So we're going to rank the 4 groups that are bonded to the chiral center, keeping in mind that higher atomic number means higher rank, and if 2 atoms are directly bonded to the chiral center and are identical, then we look one more spot down the chain until we do find a spot where we can differentiate between the 2 atoms. So I'm going to start with the chiral center on the left here, which has our chlorine, our ethyl group, and then our long carbon chain bonded to it. And if we look at the atomic number of chlorine on the periodic table, we see that chlorine has an atomic number of 17, and that's definitely much larger than the atomic number of carbon or hydrogen. So I'm going to rank chlorine here as number 1. So chlorine is going to take rank number 1 in assigning our chirality here as R or S. So chlorine is going to be spot number 1. And assigning R or S, I'm going to put that in green here, or try to. And then we need to rank the carbons, or the carbon chains that are going away from our chiral center here as rank 2 and rank 3. So I'm highlighting the 3 locations here that we're dealing with going away from the chiral center. So if we look at the position on the left here, we have a CH2 group bonded here. And a CH2 group bonded here. So then, since those 2 are identical, as we look just 1 atom away from the chiral center, we have to go another spot in order to find a location that differs between the 2. And so if we come to the next location, we have a CH3 So we have a CH3 here at the left end. And if we come over to here, we have a CH2, and then another carbon bonded to that. So going on this longer carbon chain here on the right is definitely going to result in us intersecting with a higher atomic number than if we go down that shorter carbon chain. So position number 2 or rank number 2 is going to be that group to the right. And then if we come over here to our ethyl group on the left, that's going to be ranking number 3 here. So we'll go ahead and rank that as numero 3. And remember that to assign R and S, we just go from 1 to 2 to 3 now that we've assigned the rank and our hydrogen is pointed away from us. So going from 1 to 2 to 3 it takes us in the counterclockwise direction, so we'd refer to this chiral center here on the left as being an S chiral center. So I'm just going to draw a little line to that and refer to that as an S chiral center. We can then go over to our other chiral center and also assign the chirality of that. So first off, I'm going to go ahead and erase my rankings here at the first chiral center, because we basically have to look at each chiral center separately, because each chiral center can be either R or S. Just because one of the chiral centers is R in a molecule has no bearing on whether the other one will be R or S. Alright, so I've cleaned up the structure a little bit here for purposes of going in and looking at the stereochemistry. And now that we've done that, what I'm going to go in and do is go ahead and rank the groups that are directly bonded to our second chiral carbon here, the carbon that is bonded to the hydroxy group. So this carbon's bonded to a hydroxy group, a methyl group, and this carbon chain. So ranking number 1 is the hydroxy group. Number 2 is going to be this longer carbon chain here, because you're going to end up running into atoms that have a higher atomic number as you start through that chain than if you come to this methyl group where you're just going to run into one carbon and then some hydrogen atoms, which are very, very low ranking. So, all right, now we've got them ranked 1, 2, 3. We go from highest rank, that's 1 through 2 and 3 in order. And so going from 1 to 2 to 3 takes us counterclockwise, and so therefore we'd refer to this chiral center would also be an S chiral center. So to address these questions here, number of chiral centers in this molecule is equal to 2. And assigning them as R or S, in this case we found that both of them were S, but keep in mind that it could be the case that one of them is R and one of them is S, both of them are R, whatever. All the possible combinations are at play here. So let's do one additional example to finish up looking at this concept of chirality, and that's going to be the example of lactic acid. So what is found with lactic acid is that lactic acid is a metabolic product that's produced during strenuous anaerobic exercise, and it's one of the reasons that's believed to be a causative agent of delayed onset muscle soreness and things like that, is lactic acid and some of the byproducts of that as the body eliminates that. That's going to be specifically one of the 2 enantiomers possible for lactic acid. The other lactic acid enantiomer is actually the compound that confers the general flavor of sour cream. So 2 different enantiomers of lactic acid, 2 quite different locations in which you would find those compounds and different roles that they play. And so we're going to look at the structure of lactic acid and try to assign which enantiomer is which here. And so we're going to do again a line angle formula for this. So we're looking at the enantiomers of lactic acid. And so I'll start with one of the 2 enantiomers of lactic acid here. Lactic acid, as the acid term implies there, has a carboxylic acid group at one end of the molecule. Then we have a carbon that is directly bonded to a methyl group and directly bonded to a hydroxy group. So we'll go ahead and fill that in like so. And then with the structure of lactic acid, we can also draw the mirror image of that, the enantiomers, since we mentioned the enantiomers are both present in living systems, or some living systems at least, that have very different biological roles that they play. So if we look at the enantiomer of lactic acid, drawing in the enantiomer. I'm just drawing the mirror image of this. I use that dotted pink line to illustrate that I'm drawing the mirror image on this right-hand side of the molecule that we saw on the left. So I'm trying to draw the perfect mirror image of this, which would be that. And now that we've drawn these two structures, these are going to be the two possible enantiomers of lactic acid, we need to go in and assign which one is R and which one is S. So if we look at the structure of lactic acid, we need to go in and pick out any and all chiral centers that are there. And the structure of lactic acid has only one chiral center, which I'm going to put a star on in each of these two enantiomers. Don't be tricked into thinking that that carbonyl carbon there that's part of the carboxylic acid group is a chiral carbon. It's definitely not. It never will be because of the fact that it only has 3 groups bonded to it instead of 4. So we have to have 4 separate groups bonded to a carbon in order for it to be a chiral center. So a carbon that's part of a double bond will never be a chiral center. So in assigning the stereochemistry of each of these molecules as R or S, we need to go through those rules and think about what's going on here. So at our chiral center, we have our hydroxy group. We also have, coming away from it, a carboxylic acid group, a methyl group, and then remember that there's also that hydrogen there that we're not showing, which you're welcome to fill in if you like. You don't have to fill it in though, as long as you remember that it is indeed there. And so then we're going to go through, and relative to that chiral carbon that we've put a red star on, we're going to ask ourselves what atoms are directly bonded to that chiral carbon. How would they rank in terms of their atomic number in order to set us up here for assigning these each as R or S. So coming away from the chiral carbon, in the case of our lactic acid structure, we have an oxygen atom directly bonded to the chiral carbon, which I'm showing there in royal blue. We have a hydrogen directly bonded, which I'm showing in royal blue as well. We have our methyl group, which I'll go ahead and plug in those atoms there into our line angle formula. And we have our carboxylic acid group, which I'm going to make the carboxylic acid carbon blue as well. So looking at these 4 groups, and specifically looking at the atom that's directly bonded to the chiral carbon, hopefully you recognize that the highest ranked is going to be the oxygen, because oxygen has the highest atomic number of those. And you would definitely have access to a periodic table for this. I don't expect you to memorize the periodic table in terms of which atoms are highest atomic number or lowest atomic number. So highest ranked is that oxygen. 4th highest ranked, or lowest ranked in other words, is going to be that hydrogen. Hydrogen, if present, will always be the lowest ranked if it's directly bonded to the chiral center. And then our other 2 groups here, our methyl group versus the carboxylic acid. Carboxylic acid definitely going to be the next highest ranking group, number 2 here, because that carbon in this case is directly bonded to a couple of oxygen atoms, and oxygen definitely outranks the case of this methyl group over here where we have it bonded to hydrogen atoms instead. So we'll go ahead and rank those 1, 2, 3, 4. And then keeping in mind our principle of go from the highest ranked to the 3rd highest ranked, going through number 2 on the way, and determine whether they go clockwise or counterclockwise, going from position 1 to position 2 to position 3 around that circle. That's going to take us in a counterclockwise direction, and so we would say that this molecule is S. So we could refer to this molecule as S, and the common name for this molecule is lactic acid. I don't expect you to memorize the structure of lactic acid, but if I gave you the name lactic acid and it asked for the stereochemistry assignment, that version would be the S enantiomer of lactic acid. And this is the version of lactic acid, the enantiomer, that's produced during anaerobic exercise. So this is a human metabolic product, specifically the S enantiomer is what the body is able to so-called biosynthesize. It specifically produces that enantiomer during anaerobic exercise. And so if we come over to the other molecule, verifying that this is an enantiomer, we should see that this is the R enantiomer. And so if we rank the group the same as we did before, rank 1 was our hydroxy group, rank 2 was that carboxylic acid group that's bonded to the chiral center, rank 3 was our methyl group, and number 4 was the hydrogen atom. Going from 1 to 2 to 3 takes us now in a clockwise direction, and so as a consequence of that, we'd refer to this as R lactic acid. since we're going in a clockwise direction with our rankings rather than a counterclockwise direction. So that's going to be the basic principles of how we go about assigning what we refer to as the absolute stereochemistry of the molecules, a systematic way of specifying in words what exact chirality we're dealing with for a particular molecule, so that we can distinguish in words between the two enantiomers of lactic acid, the S enantiomer and the R enantiomer. R is basically what causes the sour cream flavor. S lactic acid is what's produced during anaerobic exercise. As we transition into the next chapter where we're looking at carbohydrates, we're going to be seeing stereochemistry come into play a lot, because carbohydrate molecules will generally have a lot of chiral centers present in them, and the chirality of those particular chiral centers are going to largely determine the properties of the individual sugar, specifically how that individual sugar interacts with a biological system. So for example, if we were to look at the structure of glucose, we could ask how many chiral centers are in glucose. And in the case of glucose, what we're going to see a little bit later in this chapter 15, once we fully get into chapter 15 on carbohydrates, is we're going to see that glucose comes in two forms, what we call an open chain form that's linear, and then it could also cyclize to form a hemiacetal form that's a ring. And so I'm going to show right now just the general structure of glucose, which has a molecular formula of C6H12O6. And if we're looking at the open chain form of glucose, at one end of that open chain, we have a aldehyde group. And then coming through the chain, glucose is a 6-carbon sugar, so I'm going to go ahead and plug 6 carbons in total into my chain here. So looking at number of carbons here, 1, 2, 3, 4, 5, 6. I went 1 too far, so I'm going to go ahead and erase that 7th carbon. Didn't mean to erase all that. All right, so we have our 6-carbon sugar. And what's going to be the case is that at each of these carbon atoms, other than the one that is the aldehyde carbon, we're going to have a hydroxy group present at each one. And for now, I'm not going to show this as wedges or dashes. For now, we're just going to focus on how many chiral centers there are in glucose, rather than assigning each chiral center as R or S. So we come through here, and we put a hydroxy group on all the carbon atoms except for carbon number 1, since carbon number 1 was instead an aldehyde. We come to carbon 6, and even that carbon is going to get a hydroxy group bonded to it, so we'll go ahead and plug that in. So that's going to be the full structure of glucose, C6H12O6, without showing specifically using wedges or dashes the stereochemistry. We'll get into that detail a little bit later, but for now let's try to appreciate how many chiral centers there are in glucose, so that we can start to dive into what the chirality of these carbons is and what the relevance of the chirality is here relative to other sugars. Because what we're going to see is that oftentimes the difference between two sugar molecules, such as glucose, which obviously has a very essential biological function, and other sugar molecules which have no biological function, is often just a matter of what the chirality is at the chiral center. So let's take a look at how many chiral centers we have present in this molecule. So remember, at carbon number 1 here, definitely not a chiral center, because that has definitely not 4 groups bonded to it. It's got a carbon-carbon or carbon-oxygen double bond there. Double bonds will never be chiral centers. Position 2, definitely a chiral center, because at position 2 we have a hydroxy group directly bonded, we have the aldehyde group, we have this long carbon chain, and we also have that implied hydrogen there that I'm not showing specifically. So that definitely has 4 groups bonded to it. We can make a similar argument here at carbon 3, that that's definitely a chiral center. Same is true of carbon 4, carbon 5, and carbon 6. Oops, carbon 6 is not a chiral carbon. Take that back. So carbon 6 is not a chiral carbon. The reason is, if we look at what's present there, Keep in mind that carbon has to have 4 groups bonded to it in total. It has the hydroxy group bonded to it. It has this rest of the carbon chain bonded to it. And that means that that carbon actually has to be a CH2. And anytime you have a carbon that has 2 identical groups bonded to it, such as 2 hydrogens directly bonded to it, that carbon cannot be a chiral carbon. So number of chiral centers in glucose is going to be equal to a grand total of 4. So that's going to leave a lot of possibilities here in terms of what the stereochemistry could be at each of these 4 chiral carbons. We're going to see that glucose has a very specific stereochemistry at each of those chiral carbons, and that's something that we will continue when we dive into chapter 4. So on Tuesday, be ready for the quiz. The quiz will cover just chapter 14, which is basically everything that we've been going through for the last couple of weeks in class. It's a relatively long chapter. That includes the stereochemistry material that we talked about today, so make sure that you are up to date on assigning R, assigning S, and be ready for that quiz. It'll be the last part of the class on Tuesday. Expect that that quiz will look much like a miniature exam. It'll be about 20 minutes in length. It'll include a mixture of a few multiple choice questions at the beginning, around 3 multiple choice questions or so I would expect, and then the rest will be free response type questions, and expect for the quiz to have 3 or 4 free response problem type questions. So be sure that you're looking at those recommended end of chapter problems. Those are listed on the last page of the syllabus. Be looking at the worksheets that are available on Blackboard. Take a look at that Mastering Chemistry homework and be ready to go on Tuesday for the quiz. On Tuesday, we're also going to fully start into the chapter on carbohydrates as well. So we've teased a little bit about carbohydrates today by looking at glucose. We're going to fully get into that on Tuesday and spend basically all of next week on our carbohydrate chapter. So I will see you then, and that's it.